So I want to talk about this example and about the general foundational issues one needs to settle before one can even approach the example. So since I didn't do this last time, let me just talk about what parabolic bundles and parabolic Higgs bundles and parabolic local systems are, just because there are too many different approaches or too many flavors of these objects. I mean, they're ultimately all equivalent, but the language I'm going to use is parabolic objects. So suppose that we have a projective variety, smooth, and we have a normal crossings divisor. And I'm going to assume it's simple. In fact, I'm going to assume it's strict. So simple means that there are no self-intersections of components. Means that the normalization is the normalization. That each component is smooth, and strict would mean that there are no multiplicities. But in fact, at some point there will be multiplicities. So I'll say something about that. So normal crossing divisors with smooth components, and now a parabolic bundle on X with parabolic structure along D is, in my terminology, it's going to be this object which is going to be a family of locally free sheaves. And you can do it with general coherent sheaves, but it's trickier. So torsion frees are easy, but if they're general, it's trickier. So I'm not going to talk about that. Locally free sheaves on X. And those are, so this label, so those are parameterized by some real vector space by T, where T is really an assignment of a real number to each component of the divisor.
Non-negative or no?
Arbitrary real numbers. So this is Ti for each Di component of D. And of course, you need some compatibility between the members of this family. So there is a natural order coming from the order on the reals, just component by component, and you want ET to be contained in ET prime if T is less than or equal to T prime. You want this family to be semi-continuous, upper semi-continuous. So if you add an epsilon times epsilon in one direction, which is close to 0, you want this bundle not to change. So this is for small positive epsilon. And then you want it to be periodic in the sense that once you go across an integral jump, you just add the divisor. So ET minus delta I is going to be ET twisted by the component minus delta I. So this what this really says is it says that if you look at the cube of cube inside this k-dimensional vector space of size 1, then there are only finitely many values of ET on that cube. There are finitely many places at which those guys jump. And outside of that cube, everything is uniquely determined by twists by powers of the divisor. So notice that.
So it switches at finitely many hyperplanes?
Yes, yeah. So let me just, I mean, you know, keeping more than one component is just a nuisance. So if we just have a single component, then it's completely clear what's happening. So there is only one interval, so there is one real vector space. So we have ET, T runs in the reals, and in any interval of length 1, there are finitely many jumps for this guy that can occur, and the difference between any two consecutive jumps are always supported on the divisor. And we have.
That you didn't say, however, in the general.
No, this says it.
Okay.
Yeah, so all those bundles are isomorphic on the complement of the divisor. These inclusions are isomorphism. And so we have, I'm going to label my parabolic weights by numbers between -1 and 0. I mean, there are different conventions. I mean, you can label them by numbers in any interval of length 1. So -1, A1, A2, AS, and then less than or equal to 0. And these are exactly the jumps for this family. So ET is constant on each subinterval, and EAI modulo EAI, so it jumps exactly at A, and EAI modulo EAI minus epsilon, it's some vector bundle supported on the divisor of some rank. So, so this is a vector bundle which is a quotient of E restricted to the divisor.
Is that the consequence of what you said, right?
EAI. Say it again?
Is that the consequence of what you assumed, or you want it?
I want it. So the issue is, no, it is, if they are locally free sheaves because the divisor is smooth. So it's a codimension 1 guy. So well, let me require it. Let me require that this is locally free. I think it's a consequence, but
Now,
so
if you have two divisors, do you allow to jump on D1 plus D2 equals 1, for instance?
say it again.
Do you allow jumps on hyperplane which are not vertical or horizontals?
You know, do the jumps have to be in like one variable?
No, the jumps are in each variable separately. The jumps are in each variable separately, yeah. You could do parabolic structures when you take jumps in hyperplanes which are linear, sitting in a skew way. And in fact, in the old literature, say the works of Yokogawa and Maruyama, they did look at those when they were requiring diagonal jumps on all divisors. Those can be reconstructed from this, and actually for the purposes of non-abelian Hodge theory are more restrictive, so I'm going to stick with these guys. So this is a vector bundle which is a quotient of this. And so this is the typical description of a parabolic structure. You say that you are given a single vector bundle, say E0, on your variety, and then you're giving a filtration by vector subbundles on the restriction of that vector bundle on a divisor. And for each subbundle, you prescribe a weight, which is a real number. So that's how traditionally people write parabolic structures. But it's the same type of data. This filtration determines the nested sequence of bundles, and where the nesting jumps is determined by the parabolic weight. So these are equivalent types of data if you have one divisor. Or disjoint divisors. Huh? One component or disjoint components. So if you have one component or disjoint components, these are equivalent types of data.
I have a stupid question.
Yes.
But does anybody else have a stupid question? Sorry, a question.
Yes.
I have a question. So, suppose that I wanted to make up a notion of, a vector bundle on a variety with a divisor.
Mm-hmm.
Is there some way that I could see that this would be a natural thing?
Yeah. So let me just say, there are many. So there are theorems that I'm going to talk about right now. But let me just give you the standard example. The standard example is a real multiple of a divisor. Right? So if you take a hypersurface and you take an integral multiple of that hypersurface, you get a line bundle. If you take a hypersurface, you take a real multiple of that hypersurface, you get naturally a parabolic line bundle. So, given D, irreducible divisor, and alpha, a real number, we can define natural parabolic line bundle I'm going to call it O of alpha times D. So it depends on one parameter. And it's defined at be just D twisted by the integral part of alpha plus D. So it's a family of line bundles nested. It jumps exactly at one point, which is the fractional part of alpha in the interval 0 minus 1. Or then it jumps at all those points shifted by integers. And I need actually this, I somehow swept that under the carpet last time, but let me just give this definition and stress this out. Parabolic bundle vector bundle is called locally abelian if for these filtrations that you get on the divisor for the different components, the order in which you take the associated gradient doesn't matter. So if passing to GER along the I of E0 for different DIs is independent of the order.
Where does GER DI, GER DJ live?
On the intersection. Yeah, I mean, you take a multiple intersection, and then for all components coming into that intersection, you can the GER in many orders, and you want these orders to be, the result to be independent of the order. And there is a little lemma, which is very useful, which says that a bundle is locally abelian if and only if it's locally a sum of line bundles. So it's silly that this condition actually, I mean, so this is a condition, this is a definition that Mochizuki introduced. And it's a very natural definition, and this observation is not difficult. So there was a big issue in the non-abelian Hodge theory for many years, which is that people didn't know how to formulate even the question about matching ramified local systems with ramified Higgs bundles when we have intersecting components of the divisor. And so there were some ad hoc constructions and conditions, but nobody knew what to do universally. What conditions should we impose on the Higgs bundles or on the local systems? And what Mochizuki noticed is that this is the correct condition. So when I wrote Mochizuki's theorem last time, I actually, but the theorem really says is it says that tamely ramified, parabolic, locally abelian, local systems for which the underlying bundle is locally abelian are the same as tamely ramified parabolic Higgs bundles for which the underlying bundle is locally abelian. And that's where the non-abelian Hodge correspondence works really. Yeah.
So just make sure I understand the lemma. In this direct sum, there's not necessarily exactly one summand for each reducible divisor. Right?
No, no.
We can put them together.
Yeah, you can put them together. Yeah. So.
If you assume that the jump are rational number, is it the same as a vector bundle on the orbifold?
Yes. So I didn't say this. I mentioned it last time, but yeah. So there is another remark which is useful, and actually, when you try to prove things, it's very useful because you can do reasoning on an orbifold, understand what's happening there, and then rewrite it in the parabolic language. But so the other remark is that if the jumps are rational numbers,
Sorry, Tony, I was just
yeah.
just what's going on.
Mhm.
How can these not locally be the same thing? They're both locally free. It's
No, it's
something about the filtration.
yeah, it's all about the filtrations. These are filtered objects, and these are filtered objects, and it's a direct sum of filtered objects. And there are examples, fairly easy examples that you can write which are not locally abelian. In fact, the ones that Yokogawa studied for surfaces are not locally abelian. Yeah, but so if these are rational, we can I'm going to mess up the details, so I'm not going to write the details. The point is that you have to write them as rational numbers with the same denominator. You need to make a common denominator, write them as rational numbers with the same denominator. And for each divisor, of course. This is on a given divisor. And then there is a root stack. So we can rewrite this parabolic guy as just a vector bundle, nothing parabolic, on X with orbifold structure on D, which is Z mod R orbifold structure, where R is the common denominator of these rational guys. And by the way, the moduli spaces of such objects, they are completely insensitive of small wiggling of the weights. So you can always assume for any geometric consideration that the weights are rational. But it's more convenient to work with real ones. So vector bundles on the root stack and parabolic vector bundles are the same kind of creature. But somehow the parabolic formalism is it's a different language, but it's also a little bit more flexible. Yeah.
But the denominator can be bigger.
That's right. I mean, in fact, for different root stacks, you could get the same vector bundle theory if the stabilizers embed in each other. In fact, there is another theory which is also very useful for mirror symmetry, which says that you can take the limits of these root stacks as R goes to infinity, and you actually get a log space. So you can write all those vector bundles or all parabolic vector bundles for all possible rational weights as vector bundles on a log variety. So there is a log structure which is called Kummer log structure, which corresponds to embedding of the roots of unity inside GM, which is just the limit of all those root stacks.
These are for locally abelian. These will all be correspond to locally abelian.
Well, when there is one divisor, there is no locally abelian condition. This was just for one divisor. I mean, you can do it for, you can do a root stack with things on the different components, and then it will be a statement for the locally abelian ones. But locally abelian are the same as everything for one divisor or for disjoint divisors. Locally abelian is only about when you have intersections of divisors. Yeah. So for instance, if this divisor is divisible, if the linear system of D is divisible by R, you can think about this root stack as the stack quotient of the R-sheeted cover branched at D by the Gawa group. So these bundles are just bundles, equivariant bundles on the cover, right? I mean, so it's a very concrete thing. You can work with it. And yeah, so what do I want to say? Right, so there is Chern classes for parabolic objects. And for parabolic line bundles, so everything is set up so that for parabolic line bundles, the Chern class will be alpha times the class of the divisor. So there is the parabolic Chern 1 of O of alpha D will be just alpha times the class of the divisor. And then, of course, you can do the splitting principle yoga and define Chern classes in general for locally abelian guys. And there is a formula, which is the one needs to use in all these considerations, which is very useful. So you can think about it as the definition, or you can think about it as the characteristic class that's defined by this picture. So the parabolic Chern character of a bundle E dot is given by the integral. So I'm going to integral over all components dti. And this is, say, from 0 to 1 or from -1 to 0, doesn't matter, on any interval of length 1, but say from 0 to 1, of the Chern character of Et times e to the negative dt. And then you need to normalize by the same thing, dt of e to the negative dt. And this is with the usual disclaimer for dividing in a nilpotent ring, as we do with characteristic classes. And in fact, the top, if you stare at it for a moment, you'll notice that the top is periodic in T. So you can compute the top integral on any interval of length 1, whereas the bottom is not. So you can write this formula with the top integral in any. So this is the ER-Simpson formula. Anyway, so this is the formula. These are the parabolic Chern classes. You can rewrite them in terms of the weights, but the formulas that you get in terms of the weights are very messy. Say it again?
Matrix factorization.
What about matrix
Well, I
factorization?
mean, you have this periodic condition, right? Twisting my divisor so that things are sections after you go a couple steps. So if I think about a matrix factorization, right? I have two periodic conditions.
No, because there's no natural continuation.
I mean, the condition that you have
But
periodicity.
no, but the periodicity, these are nested things. I mean, I don't think there is a complex.
I just have one jump. Is that right?
If you have one jump,
So again, maybe two. But
I mean, even if it gives you some matrix factorization, it's going, I mean, first of all, it's not a factorization because there is no condition that the composition of the two things is the identity, right? I mean, or multiple of the identity.
So you don't have a condition on.
Or you want to say matrix factorizations with values in a line bundle, in sections in a line bundle? Maybe that will
I
work.
think what he's saying is maybe if D is actually linearly trivial, then you can think
Of this. Or if it's not, then you do matrix factorizations with. Yeah, maybe, yeah. But this would give you some homological condition on the parabolic bundle itself, right? It would say that it's an object.
And you lose the information of the real weight.
Right. And you lose the information of the weight.
At the bottom there in the formula, it's product I DTI, right?
DTI, yeah.
And I think the parameterizing is weird, but I don't understand it in the physicist integrals. So.
It's just the integral. This is how the physicists write them. Yeah,
I wonder what it was. The thing you're integrating is actually looks like
It's
the
minus
other side of the
DT.
integral.
sorry. I'm just integrating this on the cube, and this on.
Bracket is cruel.
Well, this is how the physicists write. They write their measure first, right? And
Yes, but
then,
they don't close the bracket because then the integral's down.
Right, it doesn't look like I was thinking.
I don't know.
Okay.
I mean, you know what I mean, right? I mean, it's not.
I think it's very small.
Yeah.
Now I am confused. What does E power minus dt?
This is in the cohomology ring.
Yes, but D is the sum of the di.
Yeah. The T is a vector. So this is summation di, ti, di. It's just a shortcut. You think about the T as a column vector and the D as a row vector. And okay, so let's now get to the example. So now consider parabolic rank 2 vector bundles on C, which is P1 with 5 points. And I would like those to have a full parabolic structure. So I would like, I mean, you could always assume that you have a full parabolic structure if you allow coincidence of the weights. If you allow degenerate systems of weights, then you can say that you have whatever, as many jumps as the rank. And yeah, so, or in this case, I'm just gonna, so there will be 2 jumps for each point. Different times, so different weights.
So there's 10 times in total.
Yes, so there will be 10 weights. There will be 2 weights for each point. Yeah. And in fact, as I was saying, there are chambers in the moduli space of weights. In the space of weights, there are chambers, and the parabolic bundles, the moduli spaces do not change in each chamber. And in this case, you can check easily that that the diagonal chamber, the diagonal in the weights intersects all chambers in the interior. So you could assume that all weights are balanced, that they are equal, and I'm going to assume that. So that
All weights means there are 2 different weights?
yeah, so they are for each point there are 2 weights,
Yeah.
and I can assume that that pair is the same for all 5 points. That doesn't, it's not going to change the behavior of the moduli spaces.
But the 2 things in the pair.
But there are 2 things in the pair, yeah. Yeah.
So the reason when I was taught this in kindergarten there was only 1 weight is because they did SL2 instead of
No. In fact, there is indeed only 1 weight, just because they're shifts. Yeah, they're accidental isomorphisms of moduli spaces, and in fact, the moduli space really depends only on the difference of the 2 weights. And so now again, I'm going to assume that we are looking only. So we have weights A1, B1, A2, B2, A5, B5, and
B are between 0 and 1.
minus 1 and 0. My weights are always between minus 1 and 0. And we will take Ci to be Bi minus Ai. Everything will depend only on that. And I will assume that they're all equal. It doesn't change the moduli space. The behavior of the moduli space is uniquely determined by these numbers.
The thing that changes genuinely is if AI and BI cross each other. If it try to
That's right. That's right. So the moduli space, I'm going to call it N of C, depends on C. So C is now between 0 and 1. And there are 4 chambers. I now need to look at my notes because I don't remember the numbers. Sorry. And the chambers are from 0 to 2/5, from 2/5 to 2/3, and from 2/3 to 4/5. Explain?
I mean, at least what will happen.
Yeah, I'm going to say what the moduli spaces are and what happens when you cross.
Okay.
Yeah. Yeah, it's a calculation. I mean, it's not. Right. So, so here the moduli space is empty. Here, the moduli space is a P2. By the way, not an any random P2, but it is the P2 given by this curve. It's the symmetric product of the curve. Yeah.
I'm very confused. Why is n of c not the n of c not the 1 minus c, given that I can?
No, it's not 1. There is a fifth because the shifts are given by.
Shouldn't there be a symmetry if I don't fix the window to be -1 between -1 and 0, and then instead of having a and b, I think of b and a plus 1 as my two.
No, yeah, you can always shift by an integer, but I'm doing the b minus a between 0 and 1.
Yeah,
I mean, this picture repeats once you shift.
a plus 1 minus b is 1 minus c. What's the difference between thinking of the jumps as being at a and b and thinking of the jumps as being first at b, then at b plus 1?
Well, there is no difference. The moduli space is the same.
So why is it not? Why is the picture not symmetric under flipping the two ends?
Because this is not a and b. This is.
Yeah, but so what I'm saying is
Yes.
then C becomes 1 minus C. So why are the pictures not the same for C and 1 minus C?
In this moduli space, I'm fixing also the Chern class. So this is bundles of degree 0 and yeah, of course, if you are allowing the Chern class, the Chern class of the underlying bundle to change, then you have this type of symmetry that.
So you normalize, you decide.
Yeah, I normalize which is my top bundle, whether it has degree 0 or degree 1 or degree, yeah. Yeah, so here, let's see. Yeah, so here we have degree 4 del Pezzo, a dp5. And here we have degree 5 del Pezzo, a dp4. Yeah, and so explicitly what these guys are, so this was just the symmetric product of the curve. There was the P1, right? There is a P1 with 5 marked points on it, right? So this is just the symmetric square of that P1. Now inside that P2, there is a conic, which is the diagonal copy of C. And on that conic, there are 5 points. So this guy is just the blow up of the P2 on those 5 points. And then you blow down the conic. And so when you start dealing with this Higgs picture, of course, you have to work with the moduli space in any chamber. By the way, okay, yeah, so when you start dealing with this picture, you have to work with the moduli space in any chamber. So you, for example, here you can take 1/2 and just assume that all these C's are 1/2, and that would give you the dp5. But eventually, when you try to work out the thing, everything is birational, right? You have to make sure that you have blown up all the objects in the picture so that the space is smooth, the divisor of the wobbly divisor is normal crossing, the Hecke is the preimages of the wobbly divisors both way, and the parabolic divisors in the Hecke are normal crossing. So the bigger your birational model is, the better. And presumably, you may have to even blow up that. So it's reasonable to start and work with this guy, which is the biggest one. It contains the information for all the others.
So this looks like it wants to be some sort of moment map picture and some reduction picture.
Oh, it is a moment map picture. Yeah, it is a moment map picture.
So what's the space of which these things are reductions?
It's you have these Grassmannians parameterizing the lines. They're P1s for each of the points, right? Choosing the parabolic structure just means choose a line inside each fiber.
The bundle is trivial, actually.
Well, it's trivial, or it's a bundle on P1, so you can split it. I mean, yeah, you can, right? So there is a, well, it jumps at some points, but yeah, I mean, you have a vector bundle. You have five fibers of that vector bundle, so you have 5 P1s. You have 5 lines, okay. And you're writing SO2 quotient of.
No, it's not a reductive group if you have not a trivial line, but a trivial vector bundle.
It is still SO2. The vector bundle, yeah.
You want to divide by the automorphism.
No, I don't understand what you want to divide by.
If you take, it's true. If the bundle is global, then not semi-stable, then the group has a unipotent radical, but the quotient still exists, and in fact, because of these accidental isomorphisms, you can always assume that the bundle is trivial, and you can identify the quotients explicitly. If you had an even number of points, then there will be a problem, because then there will be non-reductive quotients that are not going to be isomorphic to a reductive quotient. But anytime you have an odd number of points and something of rank 2, you have the option of tensoring with the sum of the points, and that identifies the globally non-trivial ones with trivial ones. Yeah, so this is actually one of the, this is one of the configuration. This is M05 bar. It's one of the models for M05 bar. It's one of the few cases in which it is a GAT quotient, M05 bar, M0M bar. But in fact, this model exists for any number of points. So if you take any number of points in SL2, and you take balanced weights in the generic chamber, then the moduli space is always, you take your curve, you embed it as a rational normal curve -3, and you blow up the points. It's always like that.
So there's an SO3 action on product of 5 two-spheres, and this is the.
There is, yeah.
Where is the moment space for
Pentagon space.
No, the base. This interval is what part of?
It's the product of the Cartans.
Of S, well, which is one-dimensional, which is good. But is this
Yeah, it is just
conjugacy classes in SO3 is a ray, right? Not an interval. Or is the
I think it's
where is that interval in the group acting on Hamiltonianly on these 5 spheres?
No, you need to choose a symplectic form. You need to choose a linearization. That's where this interval is. You have this space, which is P1 to the 5th, on which SL2C acts. You need to linearize the action of SL2C on a line model, or you need to choose a symplectic form.
Okay.
That's where the choice is coming from. And then you're still reducing it 0 for every choice. I mean, it's not. OK, so we are going to work with this DP5. So X is going to be this moduli space. Which is going to be N0 1/2. And in fact, it's also isomorphic to the corresponding moduli space of degree 1 with the appropriate weight here by these accidental isomorphisms. And that's going to be important because now the Hecke correspondence is going to be a Hecke correspondence from X to X. You know, when we do Hecke correspondence.
I didn't understand what this N1 means.
So this is going to be vector bundles of degree 1, rank 2 vector bundles of degree 1, with some appropriate choice of parabolic weights. I forgot, maybe it's -1/2. But it's the one which the Hecke correspondence, the Hecke correspondence will send vector bundles of degree 0. When you modify them at one point, they'll become vector bundles of degree 1. But the moduli spaces are actually isomorphic in this case. So
So N1 is both vector of degree. Oh yeah, and that's exactly the thing of flipping. So another question for you said semi-stable, but semi-stable as parabolic bundles. Right?
Semi-stable as parabolic bundles. But also happens that once we have 5 points and 1/2 and or -1/2 here, every semi-stable is stable. So there are no properly semi-stable guys in this case. And so the Hecke correspondence, which is a correspondence between X this case. I mean, of course, you need to solve the moduli problem, but then there is an explicit synthetic model. Oh, sorry, I didn't say this is going to be important. The wobbly divisor inside X is given by all the lines in X. X is a Del Pezzo of degree 4. It has an anti-canonical model. It sits inside P4 as the intersection of two quadrics. And you can look at all the lines in P4 sitting inside X.
Can you describe it in terms of the...
Yeah, so there are 16 lines, and they're described in terms of the plane model by saying it's either an exceptional divisor. So we're blowing up 5 points on a conic. So it's either an exceptional divisor, or the proper transform of a line through two of the points, or a proper transform of the conic. So these are all lines, curves of self-intersection -1, that intersects the canonical, the anti-canonical at 1. And these are all the lines on the Del Pezzo. So there are 16 of them. So I'm going to label them by Li, where I is a subset in 1 through 5 of even cardinality.
Which Del Pezzo did you have?
It's a DP5. It's a degree 4 Del Pezzo. It's a blow up of P2 at 5 points on a conic. Okay.
It's not M05. Yeah,
It's not M05. What is it?
that has recurrent number 5. Yeah, 5.
This one has Picard number 6.
Yeah.
Yeah.
This one has moduli.
Yes. But you know, our modulus is fixed because we have fixed the 5 points. And yeah, so the Hecke guy is given by blowing up X cross X in the diagonal, and then blowing up the strict transforms of the lines, line cross line. And it doesn't matter in what order, because once you blow up the diagonal, line cross lines becomes disjoint. And so the maps to X and X are obvious.
Just can you repeat?
Yeah. So we blow up X cross X in the diagonal, and then take a line cross line, cross itself in here, and look at its strict transform in the blow up. So those are surfaces inside this fourfold, which are disjoint now. And we just blow them up, all 16 of them.
What dimension do you...
This has dimension 4. The Hecke, yeah.
Oh, the curve is there also. Sorry.
Yes, the curve is there also.
Oh.
The curve is there also, yeah. So this maps obviously in 2 ways to X. Now we have to say how it maps to the curve. So that's the only thing I haven't explained. Yeah, the curve is there also. And the way it maps to the curve is, so for this you need the anti-canonical model. So you have the Del Pezzo sitting inside P4 as the intersection of two quadrics. So there is a pencil of quadrics for which this is the base locus. A pencil of 3-dimensional quadrics in P4 for which this is the base locus. There are 5 singular fibers in that pencil. So the base of that pencil is actually canonically identified with C. And the 5 singular quadrics are canonically identified with the 5 points. And then what you do is you take 2 points on X in the base locus. So these are 2 points on all the quadrics. And you look at the unique quadric on the pencil that contains the line in P4 spanned by those 2 points. So if the points are generic, there is a unique quadric. And so that gives you a point in the base of the pencil. And the map exactly blows up at the diagonal at when the 2 points are on a line which sits inside the del pezzo. And you need to check that Okay, so this is H.
Sorry, so again, the statement that this is the Hecke correspondence means if I pull that.
This is, I mean, this is the moduli space of pairs which differ at a single point at a line.
Yes, okay.
That's what the statement is. So in particular, if you take a point here, lift it here, or sorry, take a point here, lift it here, it would give you all the modifications of the bundle that you chose at all the points of the curve. So you'll get a family of curves inside this del pezzo.
Is that P1 minus those 5 points C, or is it?
No, C is P1. For me, C is P1, but you need to remember that there are 5 marked points on it.
Is this?
So you can perform the modification at the marked point?
Yes, you can. And then there is, in fact, the fiber of the Hecke is reducible when you perform a modification at the marked point, because the question is, how is the line at which you are performing the modification related to the parabolic line? Is it transversal or not? And so yeah, there are these Hecke lines, which are the fibers of H over X cross C. And they're generically P1s, but some of them are unions of 2 or 3 P1s. The point of a line cross, yeah.
Algebra modifications at that point different than at a smooth point, at an unmarked point?
Is the algebra different? Yes, because it's parameterized by 2 P1s or 3 P1s, and you can't get these extra P1s without. But that's always in the ramified case. In the ramified case, when you have parabolic structure, you need to look at.
Could you repeat what is this family of quadric?
Oh yeah, X sits inside P4, which is the anti-canonical embedding. And inside P4, it is an intersection. It's a del pezzo anti-canonically embedded in P4, so it's automatically intersection of 2 quadrics. So there is a pencil of quadrics that cuts it out. By the way, that's also useful. I mean, it's a curiosity. It's very useful for the geometric considerations, but
How the curve C appears in that description?
in this description.
Yeah.
Yeah, so there is a curiosity. If you write the pencil of quadrics as summation xi square equals to 0 and summation lambda I xi equals square equals to 0, where lambda i's are the coordinates. So there is a system of projective coordinates on this guy, because we have 5 marked points. Right, so the images of those 5 points are vertices of a tetrahedron, and so there is a system of projective coordinates. And so you can write the quadrics like that. And then if you take your del pezzo sitting here and you take the map, the degree 16 map from P4 to P4, which is the squaring of all the coordinates, then the image of the del pezzo becomes a plane. Right? I mean, it's an intersection of 2 hyperplanes. And this is Sim2 of C. And it's, in fact, the unique cover of P2, iterated double cover, iterated at all, doubly ramified at all the lines. So they're the images of the lines here. Sorry, iterated cover. So did I do?
Saying you can represent.
Yeah. 16 sheeted cover of P2 branched at 16 lines. So, well, not 16 lines. I mean, there is the configuration of they are the, whatever, 10 plus 1, 11 lines, right? I mean, there is the conic, and then there are the lines that are passing through the pairs of points. So if you take the cover which is branched at all those guys, then this is X. It's an iterated cover, but it's really a Z-mod 16 cover. I'm sorry, not Z-mod, Z-mod 2 to the 16.
In case, does H live in the product actually of X with X cross C? Or
Say it again?
does H live in the product of?
No. The map to X cross C is not an embedding.
There's a blow up.
Yeah, there is a blow up. Well, but if you add C, it could still be an embedding. But it's not. And so, okay, I'm really running out of time. It turns out that this is exactly the right amount of blowing up. So there is a parabolic divisor here, which remember was the wobbly divisor, so it's the union of the lines. There is a parabolic divisor here, which is the union of the lines cross C, union with X cross the 5 points. And the preimages of those give you, again, a normal crossings divisor here. So you've accidentally blown up enough. Okay. So their divisors called L. So this map is called P. This map is called Q. So their divisors called LPI, LQI, LLCI, and then RI1 and RI2. So I always forget the count. There's 16, 16, 16, and 10. 58 divisors. So I can say what the divisors are, but the claim is that if you take the union of all components of the preimages of the LIs and the preimages of these guys, you get these guys. So let me say what these are. The LLCIs are the exceptional divisors for this second blow-up. They're just the exceptional divisors for blowing up Li cross Li. And they're called LLCI because they really, really are isomorphic to Li cross C. They're just trivial C bundles over Li cross Li. The LPI is, so if you take the preimage of Li under the map P, it decomposes into two components, LPI and LLCI. If you take the preimage of the Li this way, it decomposes into LQI and LLCI. And if you take the preimage of X cross Pi, this gives you a divisor which happens to be reducible. It has two components. They're isomorphic, but not the same. So these are the divisors. And now, what you have to do, so the problem we needed to solve was you start with a parabolic Higgs bundle now. So this is a tame parabolic Higgs bundle on logarithmic pole. Tame parabolic Higgs bundle on C with this parabolic structure. And we want to construct f dot theta, a tame parabolic Higgs bundle on X with the divisor consisting of all the lines, so that it's semi-stable of first and second parabolic Chern class 0. So this is semi-stable. Say it again? I'm going to say that in a second. In general, you want to do it for every tame parabolic semi-stable Higgs bundle. You want to construct a guy like that so that and tame parabolic line bundle, I'm going to call it phi, with a zero Higgs field on H with all those divisors, so that, yeah, I should have started with this. This doesn't depend on these choices. This should be, once you fix the parabolic weights, there should be one tame parabolic line bundle. This is the kernel for the Hecke. The kernel for the Hecke is the trivial D-module, but because I'm introducing a parabolic structure, you need to use the identification of the category of D-modules, irreducible D-modules with twistor D-modules with a given parabolic structure. So you need to find parabolic weights for this guy, but the Higgs field has to be trivial. And it should be the same for all bundles. So that this has first parabolic Chern class 0, because it has to be feedable in the non-abelian Hodge correspondence. And this has first and second parabolic Chern class 0. And Q lower star in the Higgs world of P upper star in the Higgs parabolic world of E dot phi F dot theta tensored with phi 0. This is equal to F dot theta exterior tensored with phi dot 0.
It's a P upper star, right?
It's a P upper star, thank you. So that was the Hecke condition, but you need to parabolize it. You need to write it in the parabolic world, because it was written on stacks for D modules. Then we rewrite it for stacks and Higgs bundles. Of course, you need to make sense of these guys so that they are compatible with the non-abelian Hodge correspondence. But then this is the Hecke condition.
Wait, sorry. So this takes values in what? This takes values
Higgs bundles, parabolic Higgs bundle.
on X cross C.
On X cross C. This is a Higgs bundle on X. This is a Higgs bundle on C. So this is not phi. This is E theta, E phi.
Okay.
Yeah.
And in terms of your first talk, you wanted this would be what? This was your Langlands thing?
Yeah, this is the Dolbeau version of the Langlands.
Okay.
Yeah. Yeah. And but you need to make sure that all the operations you're doing here are really compatible with the non-abelian Hodge correspondence, and then composing the answer with the non-abelian Hodge correspondence will give you the actual Langlands thing. So this is what we did. We actually constructed these guys and these guys. The one thing, so to answer Denis' question, I'm going to assume that, the E dot is in N0 1/2. It doesn't matter, yeah. But I'm also going to make, so I really want to think about this mirror symmetry, and this actually is crucial. So the moduli space of parabolic Higgs bundles is huge. It's Poisson. And I'm going to fix a symplectic leaf. So I'm going to work with the moduli space of Higgs. So fixing a symplectic leaf just means fix conjugacy classes for the residues of phi at the 5 points. And so I'm going to require that phi is nilpotent. So in fact, it's not really, the residues of phi are nilpotent. So it's not really a symplectic leaf. It's a closure of a symplectic leaf. But in this case, it happens to be a homomorphic symplectic manifold. It's a good homomorphic symplectic manifold. It retracts on the nilpotent cone, which is in the closure. Yeah, so I'm going to assume that phi has nilpotent residues. So that's one particular symplectic leaf. In some sense, it's, closure of a symplectic leaf. It's the most complicated one. So if you look at the, if you fix the Casimirs, if you fix the conjugate sequences of the residues, the fibers of the Hitchin map are disconnected in general. And in this case, so this leaf, which is in the center of the family, this has connected fibers. So this is somehow the ramification locus for the Stein factorization of the Hitchin map.
So a basic question. So when
Yeah.
you have a nilpotent residue, once you have the residue in hand, it gives you a flag at that point.
That's right.
Is that flag the same as the one of your?
Yeah. So let me say, the Higgs bundle is parabolic, so phi has to be compatible with the parabolic structure, which means that it has to preserve the parabolic filtrations. The residue has to preserve the parabolic filtration at each point. Okay, so that tells you that the flag has to be the flag that we were given. So what this really says is it says that all such guys, they are the phi determines the parabolic structure at each of the 5 points and is determined by up to scale is determined by the parabolic structure at each of the 5 points. But of course phi has one more point at which it's nilpotent. So phi, where is phi? Phi is a map from E for any value of the parabolic level to omega 1c with poles in the 5 points. So the determinant of phi is a section in omega 1c squared with values in twice the 5 points. So this is O of 6. So this vanishes at 6 points, and we already forced it to vanish at 5 points. So there is one extra point where it vanishes. So the spectral curves for all those phi's are going to be double covers of P1 branched at 6 points, but 5 of the 6 points are fixed. They are the parabolic points. So you get, the moduli space, this nilpotent Higgs moduli space, it maps to really the sections of 6 that vanish at the 5 given points. So it's sections involve 1. Which is a 2-dimensional vector space. So this is 4-dimensional. And it's an integrable system. And the fibers, of course, are the Jacobians of these genus 2 curves, which are the curves. So each point gives you a 6 point. So you get 6 points on P1. You take the double cover branch at those 6 points. It's a genus 2 curve. That's the spectral curve.
But is it really the Jacobian or?
It is the Jacobian. Well, it's the degree 3 Jacobian, but because we have 5 mark points, it doesn't matter. Yeah. So the degree 0 Higgs bundles correspond to the degree 3 Jacobian, but we can identify it with the Jacobian.
So
Yeah.
doomsday clock is ticking.
Yes. I have to stop in 2 minutes.
3 minutes, 5 minutes.
Okay.
But so you have a first, because I'm worried with the Mukai transform, which you wanted to do.
Yes. So now we have to do Fourier Mukai. We need to do. So what's the game now? You write E dot phi as the push forward of a parabolic line bundle on this genus 2 curve. And now you have a problem because the parabolic divisor on the genus 2 curve is non-reduced. It has 5 double points. So you need to say what it means to deal with parabolic divisors, with parabolic structures on bundles, on divisors which are normal crossings but non-reduced. And you need extra data to do that. You need, for each multiplicity, to give a partition of the multiplicity. So if you remember my picture of parabolic objects, there were jumps, but if the multiplicity is, if the total amount of the integral jump is multiple, it's not 1, you can partition that integer into a sum of integers in any way you want, and then you're required to have a multifamily for that partition and jumps. And so you can think about this symplectic cliff as a specialization of a generic symplectic cliff where the divisor is actually reduced, and analyze what's happening, and you see that the partition you need to prescribe at each point is 1, 1. So you take a line bundle with a parabolic structure with 1, 1 partition, push it forward, you get this guy. Then this is a point in the Jacobian. You do a Fourier Mukai, you get a line bundle of degree 0 on the Jacobian, but now you have to take that Jacobian and map it to X. And as I said, the map is only quasi-finite, it's not finite because of these wobbly guys. And you need to resolve that map, and it does resolve. You need to, so exactly for this symplectic cliff, in general it resolves, you need to blow up 16 points on the Jacobian, which depend on the 5 points, but for this symplectic cliff they don't, they are the points of order 2. So you just blow up the 16 points of order 2 on the Jacobian, and you get a 4-to-1 morphism to X. And in fact, there is a K3 in the picture. I mean, this thing is, you can describe it completely explicitly. But there is a 4-to-1 morphism to X. So you pull your flat line bundle to that blown up Jacobian. And now you have to put a parabolic structure on the preimages of the lines. And again, this turns out to be non-reduced. So you have to figure out what the partition is, again, by specializing from the general symplectic cliff. And put an so this is what we did. We just put an arbitrary parabolic structure, chose parabolic weights arbitrary, chose the parabolic weights arbitrary for phi, and then we solve all the equations. So there were equations, Chern-Quast equations, and the Hecke equation. And they look like really horrendous quadratic and linear equations in big spaces, and it's absolutely not clear why they have a solution, but they do, and they in fact have a unique solution. So, and then you get the answer, and I'm shutting up.
Questions?
So I
Mm-hmm.
maybe just